So let's look at the energy term related to traveling wave. So here, this is something. This is a wave shape here. Let's try and understand here. And what we understood here, I hope that all of you understand. If we start oscillating one end of the string, and we can denote oscillation as like this, A and omega. Omega being the angular frequency of oscillation of one end, A being the amplitude. All gradually this oscillation gets transferred to adjoining next, and slowly it gets transferred along the length of the string. So oscillation, the disturbance, what is created at the source in form of displacement, which is oscillating displacement, travels along the length of the string at a speed called wave speed. And we have derived that wave speed. In case of a string, it is root of t by mu. That's the speed at which the disturbance or oscillation travels along the string. As it start oscillating different parts, it will acquire energy also. We'll discuss the energy terms here. So each particle on the string will have kinetic energy and potential energy. Potential energy is little more, kinetic energy is easy to understand. And this potential energy is slightly different from potential energy we had dealt with earlier. We'll try to understand what is the potential energy term here. And this potential energy, so just look at the figure here. See what happens, this is x coordinate here. So if at a particular instance, this is shape of the wave, what does it mean? The particle which was at a coordinate, let's say this distance is x. This particle which was here in the equilibrium position has displaced to this point. And the second particle which had a position of x plus delta x has moved to this point here. Let's see, this point coordinate is y position, and this is y plus delta y. This is at an instant, this is a position. So what happened there is this all particles are oscillating in which direction? In direction perpendicular to direction of the string direction, which is transverse wave. So when we look at this, let's pay attention to this particular part of the string. So if we look at initially, how was this part of the string? This was the initial part of this. We are focusing on this length of the string. And what are the length of the string when it was in the original state? This part of the string that's shown in red color, the length was dx. When this particle moves here and this particle moves here, the shape of the string becomes something like this. So what happened? Length of, since when earlier it was like a straight line, now it has become inclined, and this length will not be same as the previous length. The length of the string has changed. So potential energy is due to change in length of that part of the string. So what is potential energy? This part is what is the change in this part of the length of the string. That's what forms of energy. We'll go through very quickly. Energy terms are not so critical here. There are few terms. Okay. Now let's talk about, so all particles are oscillating, and they have all particles undergo SHM motion. And they have SHM motion. Since the motion is like SHM motion, their kinetic energy is identical to kinetic energy of particle undergoing SHM motion. So kinetic energy is no different at all. All particles undergoing SHM motion, kinetic energy depends on motion. Every particle has SHM motion. Amplitude is A, angular frequency is omega. So we understand as far as average kinetic energy will keep on changing. Most of the time we are interested in average value, as we have seen in case of AC also. This is changing so quickly, we are more concerned about average value. So what is the average kinetic energy per unit length? If we take unit length, or if we change, if we take a length equal to dx, and so what is the kinetic energy per unit length? We calculate average kinetic energy from principle of SHM. Average kinetic energy in case of SHM also is half the maximum kinetic energy. And what is maximum kinetic energy? 1 by maximum kinetic energy is, this is the term which we come. Maximum kinetic energy is 1 by 2 mu Vmax square, and Vmax is equal to omega A. Half of that is 1 by 4 mu omega square A square. That's the average kinetic energy per unit length. Only thing what you notice here, in place of m, why the mu term has come here? When you're taking per unit length, what is the mass per unit length? If I take unit length, the mass is equal to mu, which is mass per unit length. So this is an expression, and very easy expression to remember. This is average kinetic energy per unit length in case of a string which is oscillating due to traveling wave. Now coming to potential energy. See, as we look at this part also here, see, when a string is oscillating, there must be some tension. So there also tension T is acting here. Tension T is acting. And I have discussed last time also, as it oscillates, so here the tension will act tangential to the part of the string, and it should become some T plus delta T and T plus delta T. But last class also mentioned this delta T is a change in tension is much smaller than original tension, because just think of a string, don't think of oscillation as such large amplitude. This we show only for visual clarity. Actual amplitude of oscillations are extremely small. The change in tension also is small. So when it comes like this here, what is the change in potential energy is actually work done by tension force, and tension force remaining constant. So what is the work done by tension force here if the tension force is constant? So tension force work done will be equal to length, which was earlier delta x. Now the length has changed, and if we denote delta L is increase in the length, then work done will be equal to T into delta L, or T into dl. That's the work done by tension. So potential energy or change in potential energy, if that's more appropriate term, is tension into dl. And we are assuming that we should have taken delta T also, but delta T we ignore because it's much smaller than tension. So this approximation we make here, and we notice here when after this approximation, the results we obtain are still close to being correct. So T delta L is the increase in length. Which length? Earlier initial length was dx, and increase in length is delta L in the waveform. How do we calculate delta L? So what is delta L? Increase in length. Let's see how do we calculate increase in length. Increase in length is simple. If this length was delta x, if I calculate this length, new length minus original length will be delta dl. Let's calculate how do we calculate here. So what is, we will calculate this length here. Can we easily calculate this length here? So this length also, see, we are talking about very small dimensions. So when we take even delta x also tending to 0, so this can be approximated as a right angle triangle. If I take a right angle triangle, this is nothing but hypotenuse, and this coordinate is y, and this coordinate is y plus delta y. So this is delta y. So what would this be equal to? This is hypotenuse, so it is, and we take very small elements, so delta x and delta y can be taken as dx dy. So length of the deformed state, which is nothing but hypotenuse, is equal to dx square plus dy square. So what we do here, we take this dx term common. So actually you notice here dy will be much smaller than dx deformation. The amplitudes are very small. And okay, even before I go further, the derivation is not too critical. So this is a list of lesser importance. So we understand no derivation is needed, but if you understand, it's good. If you don't understand, not a problem. So if I take dx common out, what is left inside the bracket here? This is the term 1 plus dy by dx whole square, and entire thing is square. And since this term is small, basically what we are assuming, dy will be much lesser than dx. And this all comes from amplitude of oscillation being extremely small. And if you can imagine the string of a guitar, you can understand this very well. So this term becomes very small. I can take approximation, binomial approximation. So what is dl equal to? So this is the length of the deformed state. From here, I subtract original length, which is dx. When I subtract ds, only this term remains. What is this term? 1 by 2 comes here as a coefficient. 1 by 2 into dx and this term. This is the increase in length. And so what is the potential energy? I multiply by work done by tension force into dl. So this term is multiplied by T. This is the expression potential energy. And since I am calculating this is the total energy, and since it is per unit length is divided by dx here, that's why the dx term is gone. This is change in length. Per unit length we divide by dx. This term is gone. This term will remain. This is potential energy per unit length. Okay, so how do we write this one? What is T? Have we come across T term before? We know T term can be written as velocity of wave. V is equal to, velocity of wave is equal to what? Root by mu. So T is equal to mu times V square. So we have substituted T in terms of mu into V square, V being the velocity of the wave. And what is dy by dx? We have seen that dy by dx is related to dy by dt, which is particle velocity. So basically what we did, this potential energy also can be converted to terms similar to kinetic energy. So this is a term, so dy by dx also, you would have seen this expression, dy by dx is equal to, in terms of, since you are taking square, negative sign is unimportant. When you write this expression here, we notice b term gets cancelled. And what I will left with is 1 by 2 mu into square of particle velocity. This term is nothing but kinetic energy. So what is potential energy? Potential energy is equal to kinetic energy. This is equal to kinetic energy. So all we need to understand, even if you don't understand, I think few points which you should try and understand here. The reason for change in potential energy is change in length. As the length changes, work is done by the tension force. We assume it to be almost constant. Work done by tension force due to change in length results in change in potential energy. And when we calculate potential energy per unit length, when we substitute T terms in terms of wave velocity and mu, this potential energy becomes equal to kinetic energy. And this is a major difference between traveling wave and SHM motion. In case of SHM motion, potential sum of potential energy and kinetic energy is constant. Here, what it means, at any instance, kinetic energy is equal to potential energy. So for let's understand here, if the particle is here, if we take this part of the string here, what will be the kinetic energy? This part, this is at its extreme position. And when any particle undergoing SHM motion, when it is at extreme position, its velocity is 0. At this instance, kinetic energy is 0. And you notice here, and this particular state, the slope also is 0. So there's no change in length. Basically, if I change if I take this small length here, what I notice here, whatever length, here it has this, change in length is dependent on slope. If slope is 0, change in length also is 0. Okay. So here also, since the slope of this part of the string is 0, change in length is 0, so kinetic energy is 0 and potential energy also is 0. And this can be checked at any point when it comes to the mean position. And let's come to this point here. This point, kinetic energy is maximum and potential energy also is maximum. Why potential energy is maximum? Because the slope is maximum here. So key point what to understand here is potential energy at any instance unit length is equal to kinetic energy. So if I take average potential energy also will come equal to average kinetic energy. Sugnesh?
So here it doesn't obey the law of conservation of mechanical energy because there's tension force acting.
Yes. Now, see, basically what happened to keep this oscillation going, we have to keep supplying energy at the source. The work is being done here continuously.
Yes, sir.
Okay. So conservation of energy doesn't apply. Energy travels. Whatever energy is being given here, this energy travels to the string. There's no conservation of energy. And you understood here, this point here, kinetic energy, unlike SHM motion, it undergoes SHM motion. But there's a difference between the two. In case of SHM motion, sum of kinetic energy, potential energy is constant. Here, at any instance, kinetic energy is equal to potential energy. And you understand this point here?
Yes, sir.
So this happens here. Since kinetic energy, potential energy is equal, if this is the average kinetic energy, this will be average potential energy also. We can easily calculate the potential energy also. Average potential energy is equal. So total energy also we can analyze. Average potential energy per unit length, same as average kinetic energy. So what is the total energy now? If you have to calculate total energy, twice of this. So this becomes my average total energy. Very easy. And this term comes same as SHM equation. What is total energy of SHM? 1 by 2 into mass into V max square. This is same. So the total energy of any part of the string, average total energy. Average total energy means average energy in one full oscillation or over a long period of time. Same definition we have used in case of AC. So this average energy is equal to, this expression is identical to SHM equation. Though there's some differences. And if you understand this part, next term related to energy becomes easy to understand. This term you notice is the same as SHM motion. I don't have to memorize it. It is same as 1 by 2 m V max square. Now we come to some more related energy term. Okay.
Sir?
Yes?
So in the derivation, while writing TDL, what happened to the dx term?
What happens to the dx term? Okay, let's see that. What is dl here? So this I have calculated this inclined length. work done is equal to T into change in length. From here I have to subtract dx. That's change in length.
Yes, sir.
Okay, I could have written one more step. Let me write one more step here. This I am not spending too much of time because the derivation anyway people forget very quickly. So this term is equal to, I could have written a dx 1 plus 1 by 2 dy by dx whole square. From this to calculate dl, what I need to do? I need to subtract, this is the new length. This is the deformed length. I have to change in length. I have to subtract original length minus dx.
Yes, sir. Sir, actually, I have a doubt in the next step. When we wrote
Next
potential energy per unit length,
no, this is potential energy for what length? This is for length dx. I am calculating potential energy per unit length. What I
Yes,
need to do? I need to divide by dx here. That's why the dx is gone.
Yes, sir.
Okay.
So we won't take the length of the string at that instant. We'll take the length.
No, we are taking calculating. I think everything what I'm calculating per unit length.
Yes, sir.
Okay. Because problem is, see, when we take in case of SHM, mass is discrete. Here mass is continuous. So unless I define particular length, I don't know what mass to be taken. Does it make sense?
Yes, sir.
What is the length we take here? Unit length. Okay. And every time we are talking about average energy. Okay. So now energy transfer. Okay. So any instant potential is equal to kinetic energy, unlike SHM motion. So what is average energy per unit volume? That is per unit length. Per unit length, average energy was, if average energy per unit length was 1 by 2 mu, per unit volume it becomes 1 by 2 rho omega square a square. Pretty simple. Per unit volume, the same thing. In place of mu was per unit length, and mu is rho is the mass per unit volume. What is intensity? So, this when the string is oscillating, if I take any cross section, energy is passing through any cross section. Energy is passing through. So the way energy travels in case of EM radiation, like radiation coming from the sun, their electric field and magnetic field are oscillating, leading to transfer of energy. Here also when the string is oscillating, we have seen earlier also when the string starts oscillating, it imparts energy to different parts of the string. What is the energy which is flowing through? The energy flowing through, I think this is something I have done in case of intensity earlier also. When we talk about intensity what? Intensity, first I need to calculate if I take a cross section across the length of the string. And if I calculate what is the energy which is crossed in 1 second. Energy crossing it 1 second is equal to power. And if I divide by cross section area, it becomes intensity. So what is power? Power is energy crossing in unit time. What is the energy which is crossed in unit time? We have seen earlier also. All the particles which are within a length, energy which is, see, wave is traveling the speed v. So all energy which was within the length equal to v will cross through the cross section. Okay. So what is intensity? Intensity basically talks. Sorry. Okay. So if I take cross section area as unit cross section, entire energy in length equal to v, cross section area be equal to 1. This energy which is contained will pass through any cross section, and that is equal to, we have seen if you go through even EM waves also, that's how we arrive at intensity. Intensity is equal to energy contained in volume V. V being the speed of the wave. So energy contained in volume V is the intensity. Exactly same thing what we have in case of EM wave. So those who do not recall, just go to the EM wave. Again, you'll come across something similar. So this is energy per unit volume. Intensity is equal to energy contained in volume V. So what is intensity? I multiplied this term with wave velocity. The intensity becomes equal to energy per unit volume into velocity. And this term also, okay. And what is power transfer? And we have come across power term also. Power is intensity into cross-section area. So this term, if you have to take cross-section area, if you multiply by the cross-section here, so rho into cross-section becomes mu term. So power transferred is equal to this. What is power transfer means? This is the power. If this is the power transfer which is taking place in the wave, this is the also equal. And where from this energy is coming? If so much energy is flowing, all energy is coming at the source. This is equal to power at source. So whatever source of power we give, and that's what how we understand also, whatever power at source. So whatever energy which is supplied at source of oscillation in unit time, which is power, that energy is spreading out and that energy is traveling on the string. In case of EM wave, we have seen if power is given at a point source, energy spreads out over all three dimensions. Energy travels over a spherical shell kind of thing progressively. Here it travels along the length only. It is not spreading out. But expression remains something similar, what you have seen before. Again, to quickly go back, what are the energy terms we talked about? We calculated energy per unit length. What are the energy per unit length? Energy is same as, first of all, when I start with energy, I start with energy from what? 1 by 2 SHM equation. What is energy in case of an SH equation? This is energy. So in case of energy of oscillation, say energy per unit length in case of a string. When I calculate and first average energy per unit length, how should I write this expression? It is very similar expression, same expression per unit length. What I'll do here, in case since I'm writing per unit length, the mass also should be substituted per unit length. This expression becomes equal to 1 by 2, replaced by mu, and maximum velocity is equal to omega I. That becomes energy per unit length. Okay, this becomes energy per unit length. And if this is energy per unit length, energy per unit volume, multiply cross section, so mu into A becomes this is per unit length, and energy per unit volume divided by the volume of unit length. What is the volume per unit length? Volume per unit length becomes equal to cross section area. Mu by cross section area becomes equal to density. So this is energy per unit volume is equal to, in place of mu becomes rho, and intensity is energy contained in volume V. So this term we multiply by V, we get the intensity term, and we multiply intensity by cross section area, we get the power transfer. Anish?
Yes, sir.
So are you able to relate 4 terms? What are 4 terms we're talking about? Energy per unit length, energy per unit volume, intensity, and power.
Yes.
Yeah?
Yes, sir. Clear.
And we don't have, why I'm saying all this thing, if you understand linkage between all 4, there's no formula which you need to memorize. This formula also comes from SHM motion. We can write this expression per unit length. Once we can write that expression, we can write per unit volume also. If anybody has any other question, somebody has raised hand.
Can you explain the power transfer part again?
Power transfer part again. Okay, let's look at this. You see, basically what we said here, what is intensity? This is a string, and if I take any cross section, okay, what is power which is passing through any cross section? Can you tell me again what is the power which is passing through the cross section of the wire? What is power equal to?
Energy per unit time, intensity.
Into area. So basically, when the string, this is the power is energy which is passing through unit time. But where from this energy is coming? Can you think of where from this energy is coming? Think of where this energy comes from. So if I have long string, if I'm oscillating, where from the energy is coming? There has to be some source which is oscillating it here. So a person is, suppose you are vibrating the string, you have to do some work. You have to supply energy. At which point the energy is being supplied? It is being supplied at the source. So whatever energy transfer taking place per unit time in the string, that has to be equal to power of the source. Do we not do the same thing in case of EM radiation?
No, sir, I understood that, but I wanted to know how rho into A becomes mu.
Okay, this part here?
No, sir. No, sir. From intensity multiplied with area, right?
Okay. So when we multiply rho into area, what is rho into area? What is mu equal to? Tell me.
Unit mass.
Mass by length.
Yes, sir.
What is mass? Mass is rho into volume.
Yes, sir.
By length.
Okay, understood.
Okay. You understood?
Yes, sir.
Yeah, I did yesterday also. Doesn't matter. Sometimes it slips our mind, but that's a very simple expression. So it comes from this expression. Power transfer, this expression.
Sir?
And mostly what we use, if you go through questions also, most of the questions related to energy are related to simple equation that intensity is proportional to A square. Intensity is proportional to omega square A square. So normally we don't come across many questions which are based on in-depth understanding of derivation. Most of the questions are on applications, but if you understand how did we arrive at these numbers, it makes it a little easier for you to memorize it and not to make mistake while solving it. But these derivations are not too important. That's why I've done it a little quickly only. Okay, anybody has any other questions so far?
Yes, sir, I have a doubt.
Yes.
Sir, here the average energy per unit volume is the volume of the wire, sir.
Yes. Energy is contained only within the wire. Nothing is outside the wire.
Okay.
What happens? Can you understand? Do you understand the difference between this and a light source like light bulb? Light bulb is creating it creates oscillating electric field and magnetic field all points in the space. But here, where is this energy? Energy is confined within the volume of the wire. No energy is going outside the volume of the wire. Okay.
Yes, sir.
Sir,
Yes.
the average energy will be different from pi by 4 to 3 pi by 4 and 3 pi by 4 to 5 pi by 4.
Yes. And have you understood that I mentioned this part here? What is the, Ahlad, since you asked this question, tell me what will be the total energy of this part of the string here?
0.
0. So, and the same part, when it comes here, it has, what is the energy it has? It has twice the average energy. So that's why when we talk of energy, the different, when the string is oscillating, different parts of the string will have different level of energy. But if I add the entire energy contained over one wavelength, and if I divide by wavelength, even that also will come to average energy. So actually I can have time average and I can have length average. I'm not going to detail, but I think some of you understand there's a time average and there's a length average along the length also. So different, if you take this snapshot, we can calculate energy in different parts of the string. This part has maximum energy, this part has zero energy, and some part different levels of energy. We can add energy of different small elements, and after adding in all energy, basically we have taken summation of all energy, and if we divide by lambda, this also will come to the same expression, energy per unit length. It will come equal to 1 by 2 mu omega square k square. So you understand this is not time average. So energy contained over one wavelength is equal to average energy per unit length multiplied by length lambda. But if I calculate what is the, in this particular stage, Anand, have you followed this point?
Yes, sir.
Okay. Because these points are this is slightly little more complex point, and some people find it easy to understand, some find it too complex, and it is not mandatory for everyone to follow these points. Now coming to, okay, so that is what we'll keep in mind. Okay, starting from one expression, we can arrive at all. So one expression, energy per unit length, from where we can arrive per unit volume. I can calculate intensity. Intensity is equal to energy contained in volume equal to V, and then we can arrive at power output. These are the four energy terms that we should know of. Okay, and then coming to principle of superposition. What is superposition? And superposition we have also done in case of wave optics last year. Some of you may remember something and most of you may not remember much, but anyway, let's go through that part. What is superposition? Principle of superposition is very simple, and we can try and understand in terms of figure also. See, suppose there's a long string, and you understand difference between creating a wave or just creating a pulse. From this end, if I give one jerk here, and this end of the string also, we give one jerk here. And the jerk could be also some form of this. Suppose there's a vibrating fork, and this fork we just bring in contact with the wire here. What period? For a period equal to t by 2. What will happen? It will transfer this vibration to the wire. So we can create this oscillation. It is not so big. We just draw a figure like this, but actually this oscillations or transverse oscillation amplitudes are extremely small. So there's a long wire, and we create a pulse at this end. We create a pulse at this end also. And this pulse start traveling towards right, and this pulse also towards right. So the two pulse. I hope all of you understand pulse. What does pulse mean? It's not continuous oscillation, only is a very brief oscillation which is created. So this blue pulse and red pulse both are traveling. And actually, if you conduct an experiment also, what you'll find here, and since they're traveling towards each other, just like two cars traveling or two other objects traveling, and at some point they will meet. So what happens when both of them reach a common point, they tend to overlap. Overlap is, if I draw, blue color would have been like this and red color also would have like this. What you find here, when they completely overlap, the amplitude becomes sum of the amplitude of two pulses. It becomes equal to 2x. And what happens after this, after they overlap? After some time, after they overlap, again after some time we find, after the overlap is over, again we find they separate. So what we notice here, so when they overlap, still at the time of overlap, the waves do not get lost. They maintain their individual identity, and those waves emerge after overlapping is over. So it is when overlap also, it is still like presence of two individual pulses. And that's what principle of superposition is about. So let's understand, this is something, I think this is a kind of visual representation of principle of superposition. Now look at modern mathematical expression. So let's understand what is mathematical expression. If more than one wave simultaneously pass through a point, this is also like this is wave pulse. If wave, same thing will happen, similar thing will happen if these waves are passing through. The resultant disturbance is sum of disturbance each wave would have produced in absence of other. So if we have to find, so for if what will be the resultant disturbance at this point, you have to calculate. I'll calculate disturbance due to blue pulse, ignoring red pulse. And I'll calculate displacement due to red pulse, ignoring blue pulse, and add it up. That's the principle of superposition. The principle of superposition means one wave does not affect other. One wave does not affect other, and principle of superposition we use several times, is starting with so many chapters, even electrostatics also. Okay, and this principle of superposition we apply in three cases. Three phenomena are based on principle of superposition. What are three natural phenomena? And those phenomena are pretty common and has a lot of application as well. So one of them we call as interference. Second is standing wave, and third is beats. That's what this chapter is about. And first we'll deal with interference. And interference is identical to what we had done in case of wave optics. Interference will not go into much of, we will not spend too much of time. The interference topic or questions related to interference are more related to wave optics. We'll touch upon interference and we'll spend more time on standing waves. Standing waves is something we find more application of standing wave in this chapter, not in wave optics. Wave optics is we find more application of interference, and here when we talk about waves and sound, we'll deal with more with standing wave and beats. So these two will be our main focus in this chapter. We'll briefly touch upon interference, coherent waves traveling in the same direction, which was YDSE. So if you recall what was Young's double slit experiment, which was based on interference. Even if you don't remember anything about YDSE, we'll start with the assumption that you don't know anything about YDSE. And then let's see what does interference mean. Interference also is the same thing, it's principle of superposition. But in case each of the three, what is the difference between all three? Let's understand why we get three different phenomena. Because there are three different types of waves. What happens in case of interference? There are two waves, both waves, two or more waves, both are traveling in the same direction. And they reach a common point, or they come to a common point affected by two waves traveling in the same direction. This superposition of two waves traveling in the same direction. This is superposition of two waves traveling in the opposite direction. These are two current waves. Current means both waves should have same value of omega, same frequency. So this is in the same direction. This is in the opposite direction. Both have same frequency. Third case beats when there are two waves, but frequency is not same, nearly same. There's a small difference in frequency of the two waves. So these are three phenomena. Same direction, same frequency. Opposite direction, same frequency. This is two waves of slight difference in frequency. These are three applications of superposition. So let's go on now. So let's see in this case, first case, both the waves are traveling in the same direction. So how do we write those two waves? This is the equation we write in two waves. What are things we notice in case of two waves? What you notice, both waves are traveling in the same direction and omegas are same. That's an important point. Both the LS omegas are same and they're traveling in the same direction. And if we have to think of in case of light wave, this how we used to take. This is one source S1 and this is another source S2. And both are creating waves. You can also imagine this is kind of a string connected here and this string connected here. Okay, this is string, this one is string connecting from there. And this is a common point where oscillations are reaching. One is to one oscillation reaching from S1, other oscillation is reaching from S2. Okay, and we can see the angle is small. We can assume that both are traveling almost in the same direction. Angle between them is small. And what is given from the equation? What are things we understand from here? Omega of this source and this source is same. And let from S1 to P, let this distance be X1. And from S2 to P, let the distance be X2. So what do you notice from these two equations? Both sources are at same phase. They have both of here phase constant is 0. So S1 and S2, they are in the same phase at source. But we know in case of wave, as the distance keeps changing, phase keeps changing. That's a phenomenon of wave. So as the distance x, as the x keeps changing, phase keeps changing. So what will be the value of what will be the phase at point P? If I had to calculate phase at point P due to S1, in place of x, I'll substitute x1. And if you had to look at what is the phase of oscillation at P, due to second source, in place of x, you substitute x2. So what will happen when the oscillations reach here? Just look at in this particular case. In this particular case, what is happening here? When the oscillation, when this oscillation, when it reaches here, this is at the lowest extreme. This is at the lowest extreme, where other one is at the highest extreme. They are phase difference is pi. In this case, phase difference is pi. The phase difference is 0, depending on the distance. So let's understand here. So in case of interference, again coming back, the same thing here done in case of IDSC. Same thing you do in case of sound also. Two sources which are in phase are coherent sources, omega are same. Both waves are traveling in the same direction. They reach a common point P. When they reach a common point P, x1 is not equal to x2. Suppose we have taken point O here. If I take point O which lies on the perpendicular bisector, in that case, x1 will be equal to x2, hence phase will be equal. But if any other general point if we take, there may be phase difference between oscillation at P due to S1 and oscillation at P due to S2. There may be phase difference, and phase difference depends on X1 and X2. So what will be the delta phase difference here? We have seen earlier also phase difference. What is the phase difference related to? Phase difference let the point distance is X1 and X2. Phase difference between two oscillation will be equal to K times X1 minus X2 or delta X. And in this case, we could have written x2 minus x1. x2 is greater than x1, and which is delta x. What does delta x imply here? Delta x we call as path difference. The difference is path difference. This is path difference, and k term is 2 pi by lambda. So this is how this difference is related to path difference, and this is what we have done in case of wave optics also. So path difference leads to phase difference. So the two oscillations. So basically, what will happen at point P? It is equivalent to point P having two oscillations. One oscillation of amplitude A1, angular frequency omega. Second oscillation amplitude A2, angular frequency omega, second oscillation. And between them, there's a phase difference of phi. And exactly same thing get done in case of AC also. So when there are two SHM motions, what is the resultant SHM motion? How do we find amplitude of resultant SHM motion, and how do you find phase of resultant SHM motion? By taking the phasor sum. So this also interference is nothing but phasor sum. That's what we'll do next here. The resultant oscillation will be phasor sum of two oscillations. How do you draw the phasor here? So first oscillation is say A1. We'll draw the phasor for first oscillation. And second, if phase difference is phi, I'll draw this second phasor. Second phasor, how do we draw the phasor? Length of the arrow is equal to amplitude. Angle between them is equal to phase difference. And phase difference depends on the path difference. If these are the two oscillations which are reaching a common point, and phase difference is phi. Amplitude of resultant oscillation, oscillation, AR will be this. This is AR. This is like a vector sum. So AR square, this formula is nothing but same formula what we have in case of vector sum. So AR square resultant amplitude square will be A1 square plus A2 square plus A1 A2 cos phi. That would be the resultant oscillation. And exactly same thing done in case of AC also, wave optics also. But most cases, in case of light also, when we see, just try and understand here, when we see a light source, when you see a bulb, a light bulb from a smaller distance, you have a different impression. When you see from larger distance, it looks dim. Why does it look dim from the here? It looks brighter. It looks dim. Why does it look bright? Because intensity is more here, intensity is less here. Similar thing in the case of sound source also. What will happen if there's a sound source? When you stand close to the sound source, you will see the sound to be loud. And when you go far, the sound seems to be more feeble. Why it is sounding loud and feeble? This also depends on intensity. So intensity is important in terms of audio signal, in terms of light signal also. Once we calculate intensity, our interest is mostly in terms of intensity. Once we understand, and intensity depends on amplitude of oscillation. What is the formula for intensity? Intensity was equal to energy contained in volume V. What is intensity equal to? Energy contained in volume V. And what is the energy per unit volume? This was the energy per unit volume. Unit volume, that's where the density comes. And whenever it's per unit length, mu comes into V. What we notice, intensity is proportional to A square. So wherever, and so what I can replace with, so suppose I write I1 term here. What does I1 term indicate? I1 term indicate intensity created by first source. I2 indicate energy created by the second source. And IR indicate when both the sources are present, what is the resultant intensity. And every place, since it is same medium, omega is same. Sources, it's also rho is same, omega is same. And wave velocity also same. This whole thing is like a constant. I can use I is proportional to A square. Or in place of A square, you can substitute corresponding I value. And this is what we have done in case of wave also, and same thing repeated here also. So since intensity is proportional to A square, resultant intensity will be equal to I1 in place of A2 square, again using same expression I2. So in place of A1, we substitute root of I1, and this is the expression for intensity. And you may recall this expression, and those who have joined this batch late, those who have been promoted to this batch, again when we revise, and we'll go through wave optics again. So when we go through wave optics again we'll deal with this particular expression in more detail in case of wave optics. Typically, we don't come across many questions related to this concept in this chapter. So that's why I spend less time on this here. And again, when we go through this wave optics, we'll spend a little more time on this. But yeah, I think still you should be able to follow where does it come from. Vikram, is it making some sense?
Yes, sir.
Okay. So because you have not done wave optics, is it not?
Yes, sir. We have not done.
But still, this is something we have done something similar in case of EM waves, and we have done something similar in case of AC motion.
Yes,
AC also, how do we add? Basically, what was this whole thing about? If we have one oscillation like this and other oscillation, both have same omega, how do we add it up? And every point we can add it up, but that becomes cumbersome. Whenever you have to add to SHM of same omega, it is equal. We can obtain its sum by taking the phasor sum. That's the concept we are using here, which we discussed in case of AC as well. So this is an expression of intensity. Okay, and this is a phasor sum. We obtain amplitude and then we obtain intensity. Now, what will happen here, depending on and where does phi depends on path difference. So now what will happen? Phi can have different value. So when cos this expression, intensity will be maximum and cos phi is equal to 1. It is constructive means what? Constructive means cos phi is equal to 1. Then only intensity is maximum. If intensity cos phi is equal to 1, what has to be value of phi in that case? It has to be 0 or pi or 2 pi. Or you can write as, in case of constructive interference, cos phi has to be equal to 1 or phi has to be equal to 2 and pi. If this is equal to 2 and pi, if phi is equal to 2 and pi, but phi is also equal to 2 pi by lambda into delta x. What is delta x is equal to? If delta x is equal to n into lambda. So if path difference is integral multiple of wavelength, what we are saying here, if there's oscillation taking place, okay, this is a point which is the source, and this point is a distance lambda here. Whatever oscillation this point has, this also will be in the same phase, this also will be in the same phase, this also will be in the same phase. So every distance lambda, the phase remains same. Okay, every lambda phase remains same. So oscillation also, the phase remains always the same. So if it is multiple of path difference is multiple of m lambda. So let's say if this is S1, from here to this point, if this difference, this distance is say x, and from here the distance is x plus lambda. What will happen? So whatever phase this point has, from this source S2 also, the phase would be same. Phase will differ only by this path difference is lambda. So whenever path difference is multiple of lambda, they are in phase. Phase difference becomes 0 or multiple of 2 pi. So path difference is equal to n lambda. We can obtain from this expression also. So what does constructive mean? Constructive means maximum intensity. Let's again quickly look at this. Constructive means maximum intensity. When would intensity become maximum? When cos phi is equal to 1. When is cos phi is equal to 1? What is the value of phi? If cos phi 1, phi is equal to 2 and pi. If phi is equal to 2 and pi, what is path difference equal to? Phi is equal to 2 pi by lambda. So path difference becomes equal to n lambda. This is a sequence of constructive interference. And what is destructive interference? When cos phi is equal to -1. So in case of -1, similar expression we arrive in case of destructive interference. We substitute -1. So we write something like this. So we write what is maximum intensity when cos phi is equal to 1. When we substitute 1, this expression is nothing but root of I1 plus root of I2 whole square. So that's the maximum intensity. This is maximum intensity. And similarly, what is the minimum intensity? We'll substitute cos phi is equal to -1. If I put this minus sign here, this expression, I minimum intensity will become root of I1 minus root of I2 whole square. So this is plus sign, maximum intensity, negative sign, minimum intensity. Okay, and what happens if two are identical? If two sources are identical, means A1 will be equal to A2. Both have equal amplitude, but both sources have equal intensity also. So they're two identical sources. When two sources are identical, A1 will become A2. We might substitute A1 is equal to, so basically what I'm substituting here is two sources are identical, means A1 is equal to A2, which we can take as A now. There's no need to write A1 in A2. When I substitute this term also, it becomes equal to 2A square 1 plus cos phi, and cos phi is equal to 2 cos square 5 by 2. It becomes 4A square cos square 5 by 2. That's the resultant amplitude in case of two identical sources. And in that case, what would intensity be? Similar thing I can write in intensity. Intensity becomes equal to 4I into cos square 5 by 2. And depending on value of phi, the intensity will vary. Okay. And what is phi here? Phi phase difference. Phi depends on phase difference depends on path difference, which is k into delta x, or you can also write as 2 pi by lambda into delta x. This is in equal cases. What will happen now? We can take different cases. Phi can be 0. What are the important cases here? So basically, phi could, if phi is 0, if phi is 60 degree, phi is 90 degree, phi is 120 degree. So I'm taking those angles so that we know the value of half angle. See, if I take phi is equal to 30, pi by 2 become 15. That is not a round number. If I take, if phase difference is 60, this expression becomes equal to cos square 30. What is cos square 30 equal to? Cos square 30 becomes equal to root 3 by 2 square, which becomes equal to 3 by 4. So similarly, if I do that, okay, phase difference of 60, if phase difference is 60, path difference is lambda by 6, intensity becomes 3i. Intensity becomes 3i. So this is, so here the phasor will look like this. This is a phasor of first one. The second phasor will make 60 degree angle. So if a phase difference is 60 degree, path difference has to be lambda by 6. 360 degree, path difference is lambda. In 360 degree, path difference is lambda. So 60 degree is 1/6. So path difference also becomes lambda by 6, intensity becomes 3i. So if two identical sources are in same phase, intensity is 4i. If path difference as the phase difference keeps increasing, intensity keeps decreasing. So by the time phase differences become 60 degree, it becomes 3i. What will happen if phase difference becomes 90 degree? It becomes equal to cos square 45, which is square of 1 by root 2, square of 1 by 2. It becomes half of this. It becomes equal to 2i. So when two waves which are reaching have a phase difference of 90 degree, resultant amplitude is 2i, resultant intensity is 2i, I being the intensity due to each source. Next, if you look at third angle, which is important, is 120 degree. And when it is 120 degree, it becomes cos square 60. And in that case, it becomes 1 by 4. So it becomes equal to, at 120 degree, path difference lambda by 3, intensity becomes I. And what will happen at 180 degree? I'm not written at 180 degree. 180 degree, of course, intensity will become 0. They will cancel out each other. So this is constructive interference. This is destructive interference. And somewhere in between, when the constructive interference, intensity will become 4 times the intensity due to each source. And destructive interference, intensity becomes 0. In between, the intensity changes. And this is something what we have done here. And actually, this forms the key part of YDSC. Some of you recall, is it something is a repetition of YDSC? The same thing we have done in case of YDSC. And we'll not spend much time on this. Again, when we revise after finishing our syllabus, we'll spend a little more time on some of the topics which some of the students have missed, which one of the topic includes is YDSC, wave optics. Okay, so two waves. Now coming to another important thing is reflection from rigid end. See, let's suppose we have a string, and one end we apply a tension here. It is under tension, and other end is fixed. If we create a pulse, I hope by now we should understand how the pulse is created. If pulse is created, what will happen? If a pulse is created, it will keep traveling. The pulse is traveling, and it will reach the support here. And it's not that after it reaches the support, a fixed support here, it dies out. What do we find here? After it reaches the support, just like the light and all gets reflected, even this light also is a reflection of light. Light also is a wave. So when it has a reflection from a mirror, it's like wave getting reflected from a mirror. Something similar may happen in case of wave traveling on a string. When it hits a fixed support, reflection takes place, and this is the shape of the wave which gets reflected. We find what we find here. If I look at these two figures, what do I say here? What happened here? The direction has reversed and wave has inverted. Shape of the wave also has become inverted and direction has reversed. Reflection from rigid end. What is happening here? So why it is happening? One way to understand here is rigid support. First of all, how is this wave created, or how this pulse is created? Pulse is created because we apply a force at this end which has certain vertical component. Some force is necessary to which has vertical component, then only this pulse is created. So when it reaches the support also, the support has, unlike other parts of the string, support can apply force. When the support applies force, it is equivalent to the support is creating a wave. Okay. So where we interpret reflection, we think of reflection as a separate wave created by support or end. So this is called incident wave, incident pulse here in this case. This is what is incident, and this is reflected. Okay. So who is creating reflected says easier way to understand is, and this is a common way we understand here also, the reflected wave is created by support. Support exerts a force, yes.
So I didn't really understand the statement, like why should the resultant displacement be 0?
At this point, it's a fixed support.
Yes.
This point cannot move up and down.
Yes, sir.
So basically, so since the support is fixed means, so if it is like this, whether there, so how do we understand here? There's incident ray coming, or incident pulse is coming, and there's a reflector pulse. There are two pulses. This is here superposition of two pulses are taking place. The two pulses should be such that on their superposition, the displacement of this point must remain 0. What should happen in case of fixed support? Two pulses are there, two waves are there. One is incident, one is reflected. The pulses or waves should be such the resultant displacement at this point should remain 0. And we don't go into that derivation law is not necessary. Only thing is just what we need to understand in this part. What is incident wave? Having pulse, this is something we understood in case of pulse. But wave also, what has happened to one pulse, it will happen to all pulses which form part of a wave. What is wave? Wave is a sequence of repetitive pulses being created. Continuous repetitive pulse being created is a wave. So this is suppose rather than having a pulse here, this is incident wave. We are creating a wave from here. We started creating a wave. Wave is traveling from here. What happens on reflection? So something what we see here, we can write in terms of equation. Reflected wave will have this equation. What is why I suffix is used here? This will indicate incident wave. And this incident wave has some omega. It will have A, it will have A term also, 2 pi by lambda. So when it gets reflected here, and reflected support, most unless it is mentioned, we assume that there is no loss of energy. So this amplitude also is equal to same amplitude. What are two things have happened here? I can write the expression in two forms. Either I can write as minus A sine of omega t plus kx. Let's try and understand this minus sign has become plus. The minus sign has become plus because the direction has reversed. And why there's a plus sign, why it has become minus? Because ray has inverted. So this is an equation of a reflected wave. And I can write this expression in this form also. You can write as what is sine pi plus theta. Sine plus pi theta is minus sine theta. So this can be written as, so we can under this is expression. So if this is the incident wave, this is the equation of reflected wave from the support. Okay. So what we understand from here, okay, I'll just briefly mention this point. On reflection from rigid support, and we can extend this logic to denser medium. What is denser medium? Medium in which velocity of wave is lower. The direction of wave is reversed. Sign of x is changed. That's the direction reversed. And the phase changed by angle pi. We add a pi term here. So two things are happening. Rather than writing the wave is inverted, we write in terms of addition of phase pi. The pi has same effect of inverting the wave. So this is a reflection. We'll stop here and we'll continue about a reflection in the next session.
Sir?
Yes.